Okay, then welcome to the next lecture on causality for AI and ML. Today we will be looking at actual causality. So this is maybe a special form or type of doing causality and doing causal inference and reasoning. And just for your info, so this lecture is mainly based on this book, which is openly accessible by Joseph Halpern, who did the main line of research in that area. So if you want to look that up, everything you find in the lecture is probably better explained in there. And also there are talks of him giving a lecture or an introduction into actual causality. So this might be the short variant of these talks. But nonetheless, I would like to show you this like special form or like reasoning logic because it can be helpful in particular settings when reasoning about responsibility or blame or when trying to find root causes in some sort of setting. So far, we looked at do calculus, the normal Paulian framework, and usually what we were interested in was like some average effect of some change in X, like causing a change in Y. And this sort of causality is sometimes called type causality or general causality because it's the most common form. But what we have there is usually a causal graph and some sort of distribution that we assume over it. And so we talk about like the general setting. In general, like smoking causes cancer, birds can fly, whatever. But like if we are looking at a particular scenario, at a particular type of setting or variables, maybe our reasoning will divert from this like default assumptions, these default distributions, and we observe effects or causes that might not align with the average assumption. And the good thing about do calculus is, as we have seen, that it can be used for making predictions. So it sort of generalizes over like the whole class of problems or scenarios that we want to model. And actual causality is then something different, which talks about explaining causes. So it's looking backward. So do calculus might have a problem. I mean, these forms model the same type of causality, right? But the way they do it is different. But the fact that Bob smoked for 30 years did cause his lung cancer, this then requires this special counterfactual algorithm if we want to do it in like standard causal models. And if we want to do that, then again, we still make assumptions over some hidden latent variables that we might not have observed, and so on. And usually it's about attributing or reasoning about things that happened, but maybe we also want to look at responsibility for things that didn't happen, that prevented something from happening. And actual causality is this other form that then talks about a specific scenario. So I assume I observe my whole environment, which is also a strong assumption, but for simplicity, let's say we do that. And then it's about, for this particular setting of variables that we observe, can we find explanation for a particular variable taking on a particular value? So it's more backward looking. Something happened, and we want to explain why it happened. So this might be interesting in like legal settings or in court, where you have some fact or some event that happened, and you might want to decide whether someone is guilty or not, depending on maybe the assumed causal model and the information you had. So the maybe leading example throughout this lecture will be that one of rock throwing. So let's say we have Susie and Billy, and they both pick up rocks and throw them at the bottle. And Susie's rock gets there first and shatters the bottle. But just in case she hadn't hit the bottle, Billy's stone would also have shattered the bottle. And in this scenario, we assume they throw perfectly, so we have no noise or no randomness. This can be relaxed, but it makes reasoning a bit easier in the beginning. So yeah, then that's the scenario, and in the end we will look at reasoning frameworks or rules that then allow us to say, well, is Susie the actual cause of the bottle shattering, or has Billy also something to do with that? Like, how do we attribute blame and responsibility here? As I said already, actual causality uses a slightly different notation usually. So for this lecture, we will switch to that to align it better with the examples in the book and in the lecture from Joseph Halpern. And what we assume is that there is no noise, so that the structural equations are deterministic, that our exogenous noise variables are observed or can be inferred deterministically, that, yeah, they're either known and that they fully determine the system. So once we know U, we know all the endogenous variables through these structural equations. And yeah, there we know the exact value, not some sort of distribution, which we commonly do in do calculus or the Polian framework. Yeah, and for that, so at the moment we're not concerned with insufficient knowledge. We assume we have all of that, and later on, or maybe in the next lecture, we will then see how to combine those two things, how to get probabilities in there. So again, the framework is quite similar. So a causal model is here assumed to be a tuple of some signature and the structural equations. And the signature is similar to what you have seen. So it has exogenous variables, it has endogenous variables. And then it has this relation R, which basically associates every variable with a range or domain. So yeah, it's some more general type or relation on what values those variables can take on. But for our examples, of course, it does matter, but like it's not super important that's very strictly defined, at least here. Yeah, and then the structural equation. So again, it's just a fancy way of writing, saying, okay, I take all the values of my parent variables and just output the variable I'm interested in. And then something which is maybe special or what is particularly common than in actual causality is that we assume this sort of context that is almost always there, which represents a specific world. So this is similar to the counterfactual examples we had, where we not only reason over some structural causal model, but we assume a particular set of observations, and in particular this standard U without any dashes or whatever attached to it, we assume is the actual world, so the thing that happened. Yeah, and then we might want to look at this rock throwing example again and just define this causal model so that I hope there's nothing surprising. And for the remainder of the lecture, we will simply directly talk about Susie throws or Bob throws. Oh, I think in the standard example, it's Billy. But yeah, Susie is correct. The other one is either named Bob or Billy, I believe. I will correct the slides, but it doesn't matter. The variable names stay the same. And So it's some exogenous cause for Susie throwing, some exogenous cause for Bob throwing. And then if Susie throws, she hits. Also, if Bob throws, he hits. And if Susie hits, but Bob throws, Bob doesn't hit because the bottle is already shattered or broken. And depending on which of those two throw or not throw, the bottle shatters if any of those two hit. And then, as an example, the actual world we assume is that both of them throw and Susie will hit first. Then this framework usually is more on the logical reasoning side of things. So what we have is that we say, well, I have my causal model M, I have my context or world U, and this then entails some sort of logical statement, which we then later want to reason about. So this logical statement, it can either be a primitive event, so some setting of some variable. For example, if we say, well, U as T, so Susie throws is 1, then a statement that follows from it is that the bottle shatters, for example. And we can, again, assume intervention, so we also have them here, which basically is, we have a model, we have an observation, but what would be the outcome if I did intervene on some variable? And again, in the end, we can do Boolean combinations and negation and so on to not only talk about a single variable, but talk about sets of variables or like something not happening. Yeah, and then this is basically the full entailment of what the actual world models. So we have, again, the model, we have our U, and basically what this entails is that all the endogenous variables, which values they will take on. So we haven't considered interventions here, but here would be an example where Susie doesn't throw, and we observe Billy to throw the rock, but let's say Billy didn't hit for whatever reason, and this then would entail, again, because nobody of the two hits, that the bottle doesn't shatter. So this notation here with the interventions might be a bit more uncommon, but it can be transferred into like standard interventional or counterfactual operation by saying, well, the statement of intervening on Y and entailing some logical formula is the same or is exactly then true if my model under this intervention in this particular context would entail this statement. So it's basically just a different form of writing, but we usually write it like the one on the left side, because then we have a nice separation of like the actual model and the world we have observed there. And then on the right side, it's the intervened and modified thing of whatever we imagine to happen or could have happened in this scenario. And the common thing or the like whole concept, actual causality somehow evolves around is this sort of but-for test, which is this phrase, A is a cause of B if, but for A, B would not have happened. So that it's not that A has some sort of influence, of course, that can also be the case, but because we're in this logical reasoning setting, we say, well, if A hadn't had happened, then we wouldn't have seen B. And A in this scenario and also B might again be a single variable or whole sets of variables or configurations of variables that we want or do not want to observe. And then if we think about this sort of statement, yeah, we have some insights. So of course, A is necessary for the occurrence of B. So otherwise, all this reasoning wouldn't make any sense. Then in terms of implications of what sort of configurations of U we want to look at, it's exactly those ones where the statement holds true. So where from some exogenous configuration, we observe A and B to be true. And in the last case, yeah, we need to also think about what would have happened if A was not observed. But usually as always with counterfactuals, we only observe that A happened, and we then counterfactually reason via interventions that A might have not happened. And here we are also free to set some other variables. We will define that later. So we might want to introduce some other interventions too, with the fact in the end that B, due to this intervention, doesn't happen in our counterfactual model. So according to this simple test, so is A the but-for cause of the bottle scattering, we can like apply or do this testing that we saw on the last slide. And the problem here is if we take the naive approach and just say, well, let's intervene on Susie throwing the stone, the bottle will still shatter because Bob or Billy will also throw the rock, and we will observe no change in our entailed statement. So we might need to think about conditions under which we introduce additional interventions that still somehow give a consistent logic that allow us to say that Susie is the but-for cause. Because after all, I mean, I think from common understanding, we know she threw and hit the bottle, so she is the actual reason why the bottle broke. And we want our formalism to like agree with this statement. For this, there are like 3 types of rules, and we will just go through them step by step. So the first and the third one are like kind of easy or logical to understand. And the second one, this is a bit more tricky, and it also took multiple iterations in literature before they now have come up with a definition, which I think is maybe, depending on the scenarios you're looking at, might not be perfect, but at least it really covers a large set of scenarios and examples. I'm not aware that someone at the moment at least really questions the utility of the current formulation. But it might happen that someone finds a scenario where this current AC2 breaks. So that was the case for like the initial version of this second rule, where someone found a counterexample, and in particular it was this Billy and Susie throwing, which did not work out for the initial rules. So yeah, yes.
So is this a strict generalization of the but-for cause?
It's a definition of a but-for cause, like depending on how you want to see it. So some people say that but-for causes only concern a single variable. And here we say, well, it can be extended to arbitrary sets, but Tim also has better insights.
Maybe to explain a bit more, so the but-for causes are unquestioned in their nature. So like a necessary condition, if they wouldn't have happened, the outcome wouldn't have happened. And if you consider this as being the thing you won't call an actual cause, then this definition is fine. But for example, with the rock throwing example, you can find arguments for Susie is the cause because I mean she initiated like the shattering, but you could also argue in this case she isn't alone the only person responsible, because there would be another person that that would did something that would lead to the same outcome. So the other, or like there are other definitions for actual causes that try to differentiate like these cases where we might think about others being an actual cause, but there are still arguments for every possibility. So there are also like arguments bringing it more in the probabilistic setting, where the main argument is about probability raising, and this we won't discuss today, I guess.
Yeah.
And yeah, so
Yes.
yeah, it's somewhat like a generalization, but depending on the conditions, not directly.
Yeah. Yeah, right. So, I mean, so this is a very specific set of rules under a particular set of assumptions. So, for example, that we want minimality, which is rule 3. And also, really, this might be up to debate. And there is also like created forms of responsibility or this kind of setting. But here we will consider this one case where we would like to say, well, Susie actually hit the bottle, and therefore she is the sole cause for the bottle scattering. Right. Yeah. Then maybe let's look at the individual rules. So the first one I already hinted a bit about on is that for A to be a but-for cause to B, both events must have happened. So this is really, well, if either one of them didn't happen, it makes no sense to reason about what would have happened because it didn't happen. Basically, I have another slide in the end or like after that. And the third thing is really minimality. So we will try to find sets of variables that are then but-for causes. And we want to have the sets to be as small as possible as long as they fulfill the first and second rule. So this basically says, well, if I have some small set that already is considered a but-for cause, of course I can add like more factors to it, but they will basically not change the initial claim or the initial state of the smaller set being a cause already. So yeah, again, rule 1 is this relevant worlds thing where like if either the cause itself did not happen, it can just not have caused the outcome. And if the outcome didn't happen, well, then probably my X wasn't an actual cause because otherwise we would have seen the outcome. In general, if we then reason or try to find the sets, it tells us these configurations of U or settings of variables that we actually are interested in. And yeah, I said before, the third rule then is this minimality condition. If we find some small set that already is an actual cause of some outcome, then we don't need to search further. In theory, we could add additional factors, but it really doesn't help us. So for like consistency or just to have like some like unique set of variables that we consider but-for cause, we say it's the minimal one that fulfills all these rules. And so then maybe we will have a look at the original definition first that was proposed. So the first thing that we see here is that, of course, somehow we need to reason about the effect of X and of X on the outcome of our variable or statement that we want to explain. And the thing is, for that to happen, we need to consider some sort of variation. Because if the outcome never changes, we cannot reason about any effect, because we can't reason about effects that lead to a constant, like in a hand-wavy way, right? We want to have it observed that once our cause goes away, we want the outcome to also vanish. And this is basically the main idea here, that this rule like requires us that if we change X, then the outcome goes away. So right, basically it splits the variables into disjoint sets, and we allow for additional interventions, which will become important then in the next part of the rule. So we don't disallow for additional interventions, but the important thing is that if I change X, and intervene on it with, like, there is some setting of X that makes my observed effect go away. And so what you see, it's this AC2A. So this is one part of this rule. And there is then basically another one, AC2B. And for this, there exist two definitions. And those two were originally paired with this first A rule. And in the end, we will see that actually the way we have written down this rule A or part A was or is a bit problematic, which then made it difficult to define the other two parts. And in the end, we will come back and modify this A rule, and then we will also only need this one definition or this one rule to make our reasoning work. Yeah, so just in literature, you will see this part B as original and updated, like with a superscript O and U. And we will only look at the original definition because both of them are actually a bit more complex to wrap your head around, and they're anyway superseded, and the last rule is much more simple. So when we now again look at the first part of that rule, this necessity thing, we might want to consider what all of these terms mean or what those sets do. So we have that X, our observed or probable but-for cause, is part of some set C. And this is disjoint from another set W where we intervene. And in this setting, or makes it sometimes easier to think of this set that contains X to be exactly the causal paths that mediate the effect from X to our observed effect. So here it's Susie throws, Susie hits, and the bottle shattering, which basically is the path that transmits this effect. And then W is that we might want to intervene on Bob throwing or Bob hitting. So that is this initial part. And so from inverting that statement that the bottle shatters, we somehow need to find a way to block the influence of Bob throwing on the bottle shattering. So somehow we either need to intervene on Bob throwing or Bob hitting. And this formula that we will see in a moment basically allows for any subset, so we can choose freely which variables to intervene as long as we get the desired result of the bottle not shattering in the end. So this is a bit more relaxed. But on the opposite, if you might want to consider as an example of a forest fire or something that is caused by some match dropping, and in a world where there would be no oxygen, of course, nothing would burn. So in these kind of scenarios, maybe that's a good example or exercise. If you really only draw down the simple graph, you would see that this definition actually attributes oxygen as the but-for cause and possibly not the match dropping. But it's a bit weird because oxygen is always there. Of course, we can think about like what would have happened if oxygen were not there and this kind of thing. But actually, like in a court case, you would reason about whether the match was the actual cause because this other variable is basically constant and nobody changed it, nobody like intervened on it or hopefully won't intervene on it. So this initial definition is a bit strange in that regard, that sometimes it always sees these but-for causes as or these constants as but-for causes. Of course, they are required, but therefore it excludes some variables which we would maybe like to include in our reasoning or in our but-for cause. So in this set that mediates from the but for cause to the observed effect. What can happen with all of our intervening and so on, that the interventions in W that we have, that they somehow propagate causally into our actual observed causal path, and that they basically change the effect that our initial variable had on the outcome. So the thing that this like initial rule required then was that for this whole path from Susie throwing to the bottle scattering, there can be no change in all the variables that lie along this path. So basically what we say, we look at the actual world like this set star, and in our reasoning then in this rule, we say, well, for all of those variables along this path, they must take on the variables that we observed in the actual world. So whatever we do in W, whatever we intervene on there, it can't propagate into our actual causal path. And the problem with this first definition was that this set or set dash could be only some subset. So that was maybe just a flaw in the formalization in the beginning. But again, because the intention was to block all of, like, fix all of the observed causal path, this definition wasn't well formulated. So the modified version actually came in and said, well, I need to intervene on all of these variables. Exactly. So we are always in this counterfactual setting. We have some observed world. We do some interventions that might or might not be reasonable. And the question always is, under all those interventions that we do, does our reasoning still make sense? Because obviously, if we had no restrictions, we could always change the outcome by either directly intervening on the outcome, which is like doesn't tell us anything about the influence of X, or alternatively, if we just also intervened on all the parents of this phi, then we also could change it arbitrarily. So somehow we need all of those sets and just find the right conditions, which interventions we want to allow, which values we want to fix in our counterfactual world. Yeah, and as I said before, the thing is that even with these definitions, you will find counterexample where things really like don't really work out, because those conditions at the moment they correct for errors that lie along the causal path. But what happens in this rock throwing example is that still Billy will shatter the bottle, and we will see no effect. So we need an additional condition that also allows us to reason about Susie not throwing and the bottle not shattering. But somehow we then need not only to think about the causal path, the actual causal path, but also about the evidence on the other variables that don't lie along this path, because they might affect our outcome in an like unwanted way. Maybe not forget all of this, but those are basically the reasons that these definitions might be problematic. But still, we have gained some insights. We want to fix the actual causal path to the actually observed variables. And then we need to find a way to not have like all the surrounding variables change or like somehow influence the outcome from what we want to consider. And basically what people then came up with is this setting, which like just I think from the formula looks way simpler, because we only now have two sets of interventions going on. And this is then called the modified AC2 rule, or yeah, AC2A superscript M. And in general, if you take all the three rules together. So rule 1 and 3 always stay the same. And then this AC2 modified. Sometimes it's referred to as modified Halpern-Pearl definition, because like actually Julia Pearl also is an author on these papers. So yeah, it's not a coincidence that those models or those formalisms align in notation and so on. Yeah. So the thing here is, before we reasoned about things that happen on the causal path, but now we actually do it the other way around. So we consider the sets that do not lie along this path, and we require them that they must take the values we observe. So basically what this means in the rock throwing example, and we will see that in a moment, that in the actual world, we observe that Bob just didn't shatter the bottle, right? So for our reasoning to make sense, and of course, this is some assumption that can be debated. Here we would say, well, in our counterfactual scenario, he again shouldn't be the cause of this bottle shattering. So through this, like how the W is defined, we make sure that we are allowed to intervene on Bob hitting the bottle and set it to false. And then if we intervene on Susie throwing, then of course we have blocked all the, like both effects that would break the bottle, and it will stay intact, basically negating or inverting our observed outcome. Genau. And yeah, I hope it will become clear. Tim, do you think that makes sense so far? You're the expert, actually.
Intuition about this is a lot of much easier than the previous ones, because here you can basically remember that it is about freezing actual values in place. So like the witnesses or like the W's are just freezed to the values they would have in the actual world, and then you're intervening on someone as on something else. So yeah.
So basically we are freezing the whole world around the causal path. And
potentially we could, I mean, and still like a single variable could be an actual cause if like the freezing would allow it to change the value of the event.
Yeah. So yeah, the basic intuition might be that you freeze the whole world around and only leave the path from the cause to the effect open, because that needs to be able to change, because otherwise we wouldn't see any effect in the outcome. So yeah, just to have it on one slide, but yeah, this is the update. We only need a single AC rule, AC2 rule, AC1 and AC3 are fine. We don't need to change that. And so this is usually the notation reasoning framework that people use in literature nowadays. Yeah, and I think I already explained it somehow. It's quite simple. We again assume that Susie and Billy throw. Then we assume or want to look at the effects of Susie throwing on the bottle scattering. So we assign that to those individual sets. And here we set the witness to be Bob hitting. We could also set it to Bob throwing in this example. I think it doesn't make a difference. We could intervene on both, but yeah. Basically, we freeze everything that is not along the causal path from Susie throwing to the bottle scattering. Or at least we leave some path open, right? Because you could also say, well, Susie throwing, Susie hitting, Bob not hitting, the bottle scattering is also a causal path. But as we are free to define this W more or less, this yeah, we can do this or choose it that way. Yeah, then we just consider that Susie does not throw. We see that the outcome is the bottle not shattering. And again, because we talk about minimal sets, if we choose these witnesses, this W that way, then Billy is also not a cause, because that's then really standard do calculus or interventions. If we intervene on Bob hitting, we cut the relation to both of the parents, so to Susie hitting and Bob throwing, and therefore we cut off the effect or the path from Bob throwing to the bottle scattering. Yeah, and Susie then is the cause under this framework. As you see, like defining these kinds of sets can be a bit tricky. You need to like figure out which ones to intervene and like which witnesses to set. And on the other side, all of this effect propagation obviously also depends on the causal model that I have. So here, Bob throwing and Bob hitting and so on, it's also some sort of, yeah, like how do I set up my model, right? Because I could have marginalized out Susie hitting and Bob hitting, which then would leave me to, okay, whenever Susie throws, the bottle shatters. Whenever Bob throws, the bottle shatters. But I don't have these intermediate factors anymore, even though my internal logic would have still this, yeah, it would simplify, but I wouldn't be able to distinguish Susie and Bob throwing in this actual framework, because I can't condition on these intermediate factors. So sometimes it's really about also how I model my scenario. Which factors do I consider? Do I only consider the actions or some like intermediate events along the way, which might help me block off, yeah, some effects in the causal model? So that's really important here for actual causality to think of the right model, and also something which might yeah, explain a bit why actual causality and do calculus, the standard Polian framework, are considered a bit to be like distinct modeling frameworks. In standard SEMs, as we have seen before, we like a priori wouldn't know if Susie or Bob possibly throws first, right? If we are looking at temporal models. So here, actually, in a like very generic or general model, we would also need a arrow from Bob hitting to Susie hitting, which would then again give us a cycle, so which sometimes violates this acyclicity assumption. There are several ways to handle that. You can basically merge them into a single node, saying, which basically says, yeah, which one of those hits, so either Susie, Bob, or no one. Or you could just allow for cycles and then say, well, Susie suppressing the effect that Bob hits, or Bob suppressing the effect that Susie hits, depends on some sort of temporal order. So you also would need to have an additional variable which tells on you who like hits first. And then it's a contextual independency. So you have both of those arrows, but depending on which variable or which of the two hits first, only one of those arrows would like transmit a causal effect on the other one. And in general, this then is about the convergence. So it goes into, as soon as you have cycles, it goes into dynamical systems. And the thing that you then want with these causal models is that you have some configuration of of variables that aligns or agrees with all the structural equations that you have. So basically, if you have not Boolean terms, but then some continuous variable, it basically is some fixed point where your system is in a stable state that you then consider the solution or the variable configuration. But anyway, we will consider that in the next lecture, where we will just look at a few like other aspects of causal modeling and so on. But here for this actual causality, what like makes it different is really that we know how things went. We model the causal graph according to the effects or the events that we observed, and we only have this one arrow from Susie hitting to Bob hitting, or rather not hitting. Yeah, and then maybe okay, we will just have a bit of a shorter lecture and I will just finish this. There are some aspects then if you have those actual causality reasoning framework or actual causal models that you can consider. So for one, we considered in this rule 2 that we might or might not intervene on particular variables in our model. And I discussed it a bit, like if you are allowed to intervene on whatever variable, right, you can change the world as you like, right? In the most extreme case, you just intervene on every variable, like as long as it's allowed by the rules, but you can set variables as you like freely, but it's then super unlikely, right? You are not going to argue, yeah, well, if I had changed everything, then I would have gotten my expected or wanted outcome. That just doesn't make sense. And in this sort of reasoning, what people usually or sometimes consider is a sort of normality. And in that setting, the concept of defaults, which basically tells us, okay, if I didn't intervene, what would be like the expected state of my system? So birds typically fly. Of course, there are exceptions, but like without like actual evidence that I observe a penguin or whatever, I usually by default would assume that birds fly. And then this can also be related to attribution or blame and so on. So a doctor typically, because it's his job or her job, treats an illness. And I would be surprised, at least if they didn't try or didn't manage, at least for common diseases, maybe. So what this then leads us to is that we can define a particular pre-order, which basically tells us, okay, according to some sort of definition, and that's then usually the thing people argue over, what is considered common or normal, because maybe everyone has a slightly different notion of that. We can have this pre-order of worlds, which basically is really mostly the same causal model, but with different configurations of U of this variable setting that we consider normal or by default. And as I said, it might be related to morality or guilt, but it can also be expectation. So a car engine not working is maybe not the default expectation, depending on where you are. Like if you are at a car repair or whatever, then probably you see those more often. But anyway, what we would like to maybe do if we then reason about actual causes is that we want to say, well, if I do all this intervening and this kind of stuff, and this is still in the modified version of the A rule, but it applies equally to all other reasoning. is that if I do all this kind of intervening, I would like, if I want to get an explanation, I would like to have this explanation at least the same, like notion of normality, or I would want to have it to be at least as probable as the observed one. So this might also be under some sort of epsilon, so maybe I will be able or might be allowed to consider like slightly more unprobable settings. But usually what I want to have is that if I attribute something as an actual cause, I want to exclude any weird interventions or things going on that doesn't make sense and are only there to make my argument or make something an actual cause, right? Because this actual cause that I then would infer would be rejected by like the opposite side or judge or whatever. But then there is this whole discussion on responsibility and blame, which tells us, well, so far we looked at these but-for causes and set of rules and said, well, it's either variable is in that set or not. But for example, here we might want to consider a vote of where 11 people participate, and in or under certain circumstances, you would maybe want to say, well, if the vote goes through with 11-0, well, then it's really clear, but like any of those participants could have like switched their opinion and the vote would still have gone through. So maybe every one of them has less responsibility than when the vote goes with a outcome of 6-7. So anyone switching actually would have flipped the vote, right? And make it fail. So this again assumes some sort of temporal ordering. So do I know, for example, in this first setting with 11 people and the 6-5 outcome, that the vote already is at 5-5, and I'm like the last participant that votes after everyone else. So then I have a lot of responsibility and maybe also blame for the consequences. Or does everyone vote in parallel? And then again, the responsibility would be maybe distributed among the at least 6 people that voted for that outcome. Yeah, and as I said, that's maybe a bit difficult. It needs a more relaxed notion because at the moment we don't consider probabilities. And usually in this actual outcome thing, we won't consider probabilities within the equation. But what we can do is like model counting or world counting, where we say, well, maybe I don't know who voted for what. I only see the observed outcome or something like this. And then I count the worlds that lead to that particular outcome I had in the beginning. And then I can do some sort of statistics. Yeah. And again, a very naive then notion of responsibility is, okay, whoever is part of this actual causal set that basically make this event happen, I might want to assign equal probability to every one of them. And not equal probability. I want to assign equal blame to them for the outcome. And then for responsibility, I might want to look at it the other way around, actually. I say, well, some event happened, but responsibility is maybe more related to stability. So it is this set of W where I have all the witnesses or all the variables that were there, were observed, but I know my event X has changed the outcome, but how many of those variables in the environment would I need to fix to like actually make that outcome happen? So if I have a very noisy environment and my signal in this actual cause or in this actual world, like flip the outcome, maybe there were a lot of other worlds where if we assume some noise in the environment, my choice wouldn't have made a difference. So this is like a very high level, yeah, introduction there. But really the one is, yeah, how does the responsibility or rather the blame get distributed among the set of variables that are in the but-for cause, and responsibility then is like how many assumptions or how many of my other factors outside of this causal path are relevant for the outcome that I have. Yes.
So just intuitively back to the rock throwing example, we would split the blame equally between, forget names, but
Yeah.
yeah.
Yeah, actually, I think the blame would actually be on Susie only because she like alone hit. She's the single variable, or Susie throwing is the single variable in the set. But for the responsibility for this bottle shattering, it's both like for Susie we would assign responsibility of a half because we need to fix that Billy didn't hit in order to get to that outcome that we observed. Yeah. Yeah, and then for the last example, I think it's also really briefly. So all these things that we considered is cool in court cases and so on, but yeah, in computer science, usually you also have all those technical systems, you see some faults, and you want to know, okay, what was now the reason for my system malfunctioning, not working? And there, this whole topic of root cause analysis comes along. And here I only really have it on a single slide. There's a lot of literature and how to do it. But usually what you mean when you say, okay, I want to have or perform some sort of root cause analysis is that my system somehow behaves unexpectedly, that I have some anomalous events, some observations that I like wouldn't expect that are very improbable. And I might want to find a reason. So maybe there's some machine not working and it like screws up my whole production process. So all the other processing steps afterwards also fail and I observe anomalous outcomes there or like bad production quality. And I want to find the root cause that is responsible for all of this. And yeah, again, as with actual causation, maybe I want to find the minimal set because that's maybe related to cost, to sending people there to some site to fix broken machines or whatever. And actually, this is then really these sets of variables that I need to intervene on or change to make the system normal again or functioning again. Yeah. And this then is again in the notation of standard SEMs again, but really it doesn't matter that much. Basically, if we already have a causal model, we are kind of lucky because causal models already tell us what to expect in terms of distributions, in terms of joint distributions and also conditional distributions of our variable. So we might have observed our system before and we know the expected joint distribution over all the variables. And we then will observe like a particular set of values. And we will see for certain variables that they drop below some probability threshold according to our causal model. And the question that we then always need to ask is whether this out of distribution value, is it due to anomalous parents? So did I at this particular variable get some values that are just weird coming in from the parents, and that throws off my value here and lowers my probability? Or is there some effect, some external noise, some whatever happening at this exact location, which leads to these outliers? And basically, again, in a very naive way, SEMs are perfectly suited for this because we can just look at the conditional probability, which we have through our structural equations, and say, well, if I look at this conditional probabilities of my observed variable or value given all my parents, if that adheres to the expectation of my causal model as defined by the structural equation or conditional probability tables, then this particular variable follows its local process and might be fine. So the effect comes from some of the parents. And if I get a low probability here, then it diverts. I will correct this typo. But then it diverts from this expected conditional probability. So how I would compute my variable normally. And I have some unobserved noise variable that, for example, is added at the end, which then really throws off the value I observe. So really what I do is I take all the parent variables, compute the expected outcome of my variable, and then compare with what I actually see. And if it's too far off, according to the distribution of my structural equation, then I conclude that it's the noise term that I don't see that led to this problem or this low probability situation. Right. Again, marginal probabilities might be interesting because it tells you if you're doing analysis which parts of your system, of your production line or your web server, web services might be affected. And the conditional probabilities then can help you to find the actual causes, which are usually a subset of those other variables to find where to intervene or where to send your engineers. But yeah, that's it. Thank you and see you next week.